Okay, so let's look at another time to station problem. This one has a relative bearing change of 45 degrees, which is a lot more than we've seen in any of the other time and distance to station problems. So the other methods, the approximation formula used to solve the other types of problems tends to choke when you have large changes in bearing. And this is a bit of a special case if you're using that method. But if you're using the triangle method, if you're just drawing it out and solving the triangle, it's not a special case. You just do this problem the same way you would do any other time and distance to station problem. So let's see how that goes. Just start by drawing the aircraft's initial position, which is from a 045 or with the nav aid on a 045 relative bearing. And it flies until it gets the nav aid on a 090 bearing. And that takes 5 minutes. So we overlay the triangle and solve for our, well, we already have our angle, so we solve for our side that is adjacent to the angle. That's our distance to the nav aid. And we have everything we need. So we've got our angle, we've got our side opposite the angle, and we're looking for our side that's adjacent to the angle. So those three things are what make up the tangent function. So we plug in our values. 45-degree angle, 5 minutes is opposite, x is adjacent, solve, and we get x is 5 minutes. Easy enough. We go back to our question, we look, we see one of our choices is 5 minutes, and it is correct. So, no big deal. But then when we look at the solution, we see that the FAA recommends a different way of having done the problem. And it says that when a relative bearing doubles in a specific time, the time to the station is that time, meaning the time to double the relative bearing. Thus, the time to the station is 5 minutes. So let's go back and look at what that meant. So what happened here is the relative bearing doubled. It went from a 045 to a 090. So they're saying that this is a special case where if your relative bearing doubles, then your time it took to double the bearing is equal to your time off the station. And it turns out that that special case is true because the tangent of 45 happens to be 1. So in this case, you've flown until you reached a 45-degree change in bearing, so you've resulted in your tangent value is 1, and then when you solve it, it winds up being an isosceles triangle. So it's a special case. You can only use it when your relative bearing doubles. The nice thing about the triangle method, though, is it doesn't care if your relative bearing doubles. There are no special cases. Just solve the triangle. So what happens if you weren't using the triangle method and you forgot that this was a special case? What if you used the approximation formula that was presented for solving all of the other time and distance to station problems? Well, if you used that formula, you would plug in the minutes flown and the bearing change. Well, the minutes flown was 5, the bearing change was 45. Do the math and you get 6.66 minutes. The problem is that's not even close to 5. That's way off. So your answer is wrong. And it's not only wrong in real life, it's also even wrong in the test because this was a special case. The reason this was a special case and the reason that the formula didn't work is because the 45-degree change in relative bearing breaks the approximation formula. The approximation formula fails when your relative bearing, or well specifically it fails anytime you get significantly away from the abeam point of the nav aid. So when the direction that you're flying is no longer, tangent to the circle that encloses the nav aid, if you can visualize that. As you get farther and farther off that abeam point, the approximation becomes less and less true. So for a 45-degree change in relative bearing, you're not going to be able to use that approximation. And you're going to have to rely on the special case that was presented as the solution, which is a doubling in relative bearing results in a equivalent time to the station that it took to double the relative bearing. But if you're using triangles, none of this matters. Just solve the triangle and you're done.